Tennessee River is now a chain of lakes, changed from a flowing stream by the construction of a series of dams. The newest dam is near the confluence of the Tennessee with the Ohio River and creates Kentucky Reservoir, the largest in the Tennessee Valley, 184 miles long with more than 2,000 miles of shoreline. The construction of the huge Kentucky Dam, built for the storage of floodwaters, for navigation, and for the production of electric power, was expected to bring about many biological changes in the area, one of which was the creation of favorable conditions for the production of Anopheles quadrimaculatus, the vector of malaria in the southeastern United States. This reservoir was to be impounded in a region where abundant vegetation and a mild climate had long been associated with the occurrence of malaria in partially cleared and poorly drained bottomlands, sloughs and swamps along the Tennessee River. Such areas, subject to periodic flooding, quickly grow up in willows, buttonball, and luxuriant stands of annual plants which create an ideal environment for the production of anopheline mosquitoes. While reservoir improvement eliminates many floodplain swamps and other low-lying problem areas, broad shallows will be created in many localities along the reservoir margin, where vegetation control will remain a problem of major concern. Detailed study of the topography of the Kentucky Reservoir region was the first step taken by the malaria control staff of the Health and Safety Department in the development of plans for malaria control in the region. The sanitary engineer in charge of malaria control, together with the medical malariologist, the biologist, and others, planned the course of action. For to specialists trained in malaria control, the 2,000 miles of shoreline presented numerous challenging situations and many troublesome spots where malaria had long been endemic. These had to be located before malaria could be successfully controlled on the reservoir. Preliminary fieldwork included a botanical reconnaissance of the reservoir basin, for mosquito production is influenced by the types of plants which occur in a potential breeding area. Adult mosquito catching stations were set up in barns where Anopheles quadrimaculatus commonly rest by day. These stations were periodically visited to obtain an index of mosquito population, which served as a guide in program planning. All likely breeding places were located and charted. Particular attention was given to extensive swamplands and other marginal depressions which might hold water after impoundage. Periodic dipping for larvae in likely breeding places provided information which, together with the records of the adult catching stations, furnished a base of reference concerning the malaria potential before creation of the reservoir. Health offices in the region participated in program planning by providing information concerning past outbreaks of malaria. Available morbidity and mortality records were analyzed to gain this information. Families were informed of the importance of the survey and usually responded cheerfully to the requests for blood films. The films were prepared by the health department nurse, who knew the residents through previous contacts. Upon completion, slides were forwarded to the laboratory for examination. Information secured from adult mosquito catching stations, from larva dipping counts, from tabulations of aquatic plant life, and from malaria surveys, was analyzed, correlated, and plotted on detailed working maps when the field force reassembled after the completion of preliminary field appraisal. Experience in the Tennessee Valley demonstrated the futility of attempting to control anopheline mosquito production in reservoirs of this type entirely with larvicides. A new concept was developed, which involved the engineering application of permanent works. The Engineering Project Planning Division of the Water Control Planning Department collaborated in the selection of the type of engineering project best suited for the permanent control of problem areas located by the Health and Safety Department staff. Where diking and dewatering was selected as a means of control, this division furnished cost appraisal analyses and preliminary plans for dikes, pumps, and pump houses. 22 miles of dikes were planned to cut off large flat areas from the main lake. Assistance was also given in planning the large-scale earth movements required in filling and deepening and in extensive drainage projects involving the removal of more than 2 million cubic yards of earth. In many instances, the Highway and Railroad Division was able to relocate railroads and highways within diked areas. This eliminated the necessity for flat slopes and expensive riprapping for protection of fields against wave action. The resulting savings in construction and clearance costs more than equal the cost of building the dikes. The Reservoir Clearance Division prepared the reservoir in accordance with specifications based on the impounded water regulations of the state health departments. Many refinements in reservoir preparation practices were developed through close cooperation between the malaria control staff and the clearance division. The Biological Readjustment Division is interested in developing fish and wildlife resources, just as the malariologist is interested in reducing mosquito production. By planning and working together on problems involving both interests, many of the apparent conflicts between mosquito control and wildlife conservation can be resolved. Malaria control projects were reviewed with the Construction and Maintenance Division for inclusion in the overall reservoir construction. The Regional Studies Department reviewed alternative plans for the use of marginal lands in the reservoir area. For example, the decision to protect the town of Big Sandy against backwater by means of a dike was closely related to malaria control plans for a nearby dewatering project. it was proposed to limit human occupancy of the restricted areas to the hours between dawn and dusk when malaria mosquitoes commonly do not bite. This, however, permitted normal agricultural use. Based on the findings of the field staff in the reservoir area, these proposals were drawn up as a preliminary report outlining a suggested malaria control program embracing permanent shoreline improvement measures in Kentucky Reservoir. The field staff reviewed the important features of the report in its final form. Due to its size, flat topography, and limited scope of water level fluctuation expected during the mosquito breeding season, this reservoir will present an unusually serious and extensive malaria problem. Portions of the reservoir cannot be effectively and economically controlled to prevent mosquito production by the usual measures applied after impounding, namely the application of larvicides, annual growth removal, and marginal drainage maintenance. Approximately one-third of the shoreline was classified as areas where prolific production of mosquitoes was expected to occur under conditions difficult or impossible to control by the usual methods. It was for these areas that permanent improvement measures were proposed. Estimates of the initial cost of these projects, diking and dewatering, deepening and filling, land use restriction and mosquito proofing with limited larvicidal operations and shoreline maintenance, when compared with the initial cost of the usual control measures, indicated that a greater capital investment would be required. However, in the annual cost year after year, the economic value of the proposed plan is seen in the difference between $333,300 and $165,580, or $167,720 in estimated annual savings. So it was planned to do a better job at a greatly decreased annual cost by using permanent works. The Director of Health saw in the proposed program the opportunity to demonstrate the application of permanent works in the control of malaria on impounded water. The proposal was in agreement with the opinion of the Board of Consultants, who from time to time had suggested that more economical and permanent approaches to malaria control should be formulated and applied on impounded waters in lieu of less effective methods involving high repetitive costs. The proposed plan was carefully examined for agreement with state regulations governing impounding of water and forwarded to interested agencies for their consideration and criticism. Endorsement of the plan was received from the State Department of Health of Kentucky, from the Surgeon General of the United States Public Health Service, from the Tennessee State Department of Public Health, and from the International Health Division of the Rockefeller Foundation. The proposed plan for malaria control on the Kentucky Reservoir was submitted by the Director of Health through the General Manager to the TVA Board of Directors for approval. The Director of Health subsequently was advised that the General Manager and Board of Directors approved the principles for malaria control on Kentucky Reservoir, which had been developed over a period of 4 years of engineering, biological, and medical study. Initial steps in the preparation of the reservoir include staking the contour, marking the limits of the reservoir. Normal pool elevation is marked as the basic clearing line for applying specifications for the removal of trees and brush. The distance to be cleared beyond this line varies with topography, type of growth, and exposure of the future shoreline to wave action. Most of the workmen were residents of the area, familiar with the use of timber cutting tools from their boyhood days. Various types of tools adapted to specific operations were required. At the beginning of each day, assignments were made, tools were selected, and the men began their work. The underbrush was cut by one crew to make it easier and safer for the timber cutting crew which followed. Felling of the larger trees is a hazardous operation, requiring skill and constant precaution to assure safety. In some areas, mules were used to drag logs into the cleared area, where they were piled. Along stream banks, large trees were dragged from the water's edge by tractors with winch attachments. Special bank machines developed within the authority were also used on this type of operation. Marketable timber was hauled to sawmills and cut into lumber. On all operations, care was taken to provide the workmen with an ample supply of safe drinking water. Paper cups were provided at all times, and only chlorinated water was distributed. At regular intervals, field tests for residual chlorine were made. A testing solution was added to the sample, then checked against color standards to give an estimation of the residual chlorine. These safety efforts resulted in a very low accident frequency rate. Trees in the upper limits of the fluctuation zone of problem flats were cut level with the ground. This not only facilitates the use of power mowers in annual growth removal operations, but also reduces resprouting. Because of their tendency toward excessive resprouting, willow stumps were treated with an arboricidal oil. Where ground conditions were suitable for the use of heavy equipment, timber and brush were cut, and especially designed power rakes were used to push the cuttings into windrows for burning. Occasionally, it was necessary to sever large branches from the trunks and to cut trees into 2 or 3 sections in order to secure compactness necessary for burning. No other manual work was required. The sweeping action of the limbs and brush as they're pushed along gives an unusually clean job. The power rake consists of a conventional bulldozer with flexible teeth hung on the blade and with supporting slides on each margin to keep the blades at the proper working elevation. The long windrows of brush and trees were allowed to dry thoroughly before they were burned. In the final stages of burning, smaller power rakes pushed the remaining material together to assure complete disposal. The end result of this operation is a clean ground surface. Boat channels were marked in areas where post-impoundage larvicidal operations were anticipated. Locations for channel markers were established by field surveys. Plans for these channels were coordinated with other reservoir navigation aids. The markers also provide aid to fishermen and operators of small recreation boats. Drainage ditches were constructed in order that swamps and other low-lying areas along the margin of the reservoir would be completely drained at the time of low water levels or would fluctuate freely with changing reservoir levels. Field surveys provided basic information for the development of drainage plans. After drainage plans were approved, ditches were staked. Construction was done usually with drag lines. Where ditching was in wooded areas, stumps were removed by blasting. The shattered stumps were removed with the aid of timber hooks attached to the drag line. In swampy areas, the drag lines traveled and operated on supporting mats. In some situations, drainage was required for clearing or other construction work which would have been impeded by ponded water. final conditioning of the malaria control fluctuation zone required the removal of vegetation from a marginal band which varied in width from a few feet on steep banks to a wide belt in the flats. Where topography, the type of growth, and weather conditions permitted, area burning was utilized in marginal growth removal. Some woody stands were burned over, but most area burning was over grass-covered flats. In situations where area burning could not be utilized, hand and machine cutting was used prior to raking and burning. Immediately below the margin of complete growth removal, tall vegetation extending into the fluctuation zone was topped. In some cases, mowers and teams belonging to local farmers were utilized on the growth removal operations. Team mowers were especially useful on rough terrain and in small areas. Tractor mowers cut from 2 to 4 times as much per day as team mowers and were used principally in large flat areas. Although low stumping added to the initial cost of clearance in the fluctuation zone, the increased effectiveness and economy of the mowing operation and annual margin conditioning repaid this additional expense. Hand cutting was used where more economical methods could not be applied. After cutting, the brush was piled for burning. To reduce man-hours required to clear areas of heaviest regrowth, hand cutting of sprouts was preceded by a brush harrow drawn by a bulldozer. After the harrow had passed over the area, the remaining sprouts were cut by hand and piled for burning. The piles of brush were burned. Thus, reservoir preparation provides a clean basin at the time of filling, an essential factor in the control of malaria on impounded waters.